for 2021, and it's regarding improvements that we're planning on doing at Long Pond to improve the water quality. We have two guests tonight. I'd like to introduce Rich Gullick, who is our consulting engineer, worked closely with us regarding the discolored water situation. He will discuss the background on manganese, what we did to identify the problem. And then we have Jack Cangione, who is from Koch Industries. He will be doing a presentation about the system we're looking at to rectify the discolored water. In addition, it will deal with filter issues. We have slow sand filters that were built in 1939. They've been working well, but DEP has questioned their efficacy. And the system that Koch has would actually address both the manganese and the filter concerns. So that will be second. Welcome, everyone. Rich, if you'd like to begin.
Sure. Thank you, Jim, very much. I'm going to give a little background for anybody who's new to the issues that we're discussing here tonight. So the colored water episodes have gone back for several years. August of 2018 came on relatively severe with some discoloration, yellow to brownish water, hit the newspapers and so on. Certainly caught DEP's attention. Housatonic's been doing a very regular monitoring program through several distribution sites since then. I started working with Jim Mercer and Housatonic back in 2019, looking at disinfection procedures and evaluating the lead and copper rule compliance. Monitoring is going on for color, but nothing much had come up other than a sample back when they first started with that monitoring in 2018. Then the color returned in July 2020, again, fairly strongly in places. Some of that we believe was both coming from the plant and some stirred up in the distribution system during some of the flushing periods. So I got involved with that at that time also. We knew that by history at least, it had been thought that iron coming from old corroding pipes is the main issue that was causing the discoloration, but I wanted to look into manganese because that's always a possibility for that. Jim mentioned that some of the pipes that had been taken out were totally clean after they had a break and taken out some pipes. They were very clean, so that made me really wonder if it was really old pipes that were deteriorating so much. And then when Jim told me that he'd had yellow water had actually come out of the treatment plant, I realized then that it was most likely manganese. So I'd already been trying to get Housatonic to hire an expert in corrosion control to look at the copper and lead. And it was a perfect time to do that, along with looking at manganese and iron. So I referred Cornwell Engineering Group to Jim Mercer of Housatonic, and he contracted with them to do a study on these different metals, lead, copper, and manganese and iron. And just as for full disclosure, I used to work with them. I partnered with them on a research project. Then I actually worked for them as an employee. Then I hired them twice while I worked for other water utilities, They were my consultant, including a big lead and copper project. So I know how good they are. I was very glad Jim brought them on board. So more data had been acquired during that colored water episode. Looking at those data and other factors involved, it became very clear that manganese was the issue. It was not iron. We would detect low levels of iron all the time. And whenever there was colored water, the manganese would be elevated. So manganese does cause color ranging from yellow to brown to gray to black, depending on how much there is and how much has been oxidized. So it can actually be different in the distribution system. They come out of the treatment plant, and once the chlorine hits it, that's when it goes from a dissolved to a non-dissolved or particulate state as it gets oxidized and where it creates the color. So with that in mind, one of Cornwell Group's main recommendations was to remove the manganese. Let's try to stop that yellow water from getting into the system and reduce the deposits that also get onto the distribution system pipes that can break off during hydraulic turbulences and create really dirty water. And some of the darker colors are typically more from that. With that in mind, Housatonic hired Lennard Engineering, their regular local engineering firm, to do a feasibility study, and that was conducted, and different techniques were looked at, including a manganese green sand, a green sand plus, which is a kind of an oxidative filtration system, They looked at another system that really didn't pan out. We'll slide right by that. And then also looking at a membrane system, as opposed to normally when you want to remove manganese, you need to oxidize it, often with chlorine or some other oxidant, and then remove it from the filters. You can't add chlorine before the current filters because these slow sand filters are biological. There's a lot of microbiological growth in there that are helping remove the contaminants, and the chlorine would kill that. So that won't work. We need a different system, and what's been proposed here by Leonard Engineering, working with Koch Industries, that's hopefully I'm saying all this right, who's going to be speaking in just a minute regarding the actual ultrafiltration technology. What they'll do is they would chlorinate the water, just like we would have otherwise, and then these ultrafiltration filters will replace the slow sand filter. With that in mind, I would like to make a comment that in my review of the filters, and looking at these, based on my experience with filters and water chemistry knowledge, I did not see anything wrong with them. The data looked great. I don't accept what BEP was postulating about them. Nonetheless, the ultrafiltration filters would most likely do a better job of filtration removal. And that's what they've been shown to do. So it sounds like it's going to be a great system. So it's an upgrade, I would say, of the slow sand filters. And then the rest of the clear well, the chlorine contact chamber, and the storage tank all stay the same. So just to reiterate, again, we're trying to get the manganese out from the treated water, and also that will prevent further deposits forming in the distribution system over time and help give you all the cleaner water. And Jim, I guess that's my intro. So if you want to slide it from there to Jack.
Yeah, thank you. Thank you very much. We also have engineers, Leonard Engineering, who looked at the whole process as well. They evaluated different systems, and they really looked at three different systems, and they decided that Koch Industries had the best system that would both remediate the manganese and deal with a slow sand filter. So I'd like to introduce Jack from Koch. Jack?
Hey, good afternoon. Thank you, Jim and Rick, for introduction. And if you could allow me to share the screen, I can get a little presentation going. So I have a short PowerPoint. So just a little history on who I am. I'm Jack Hangiano. I've been with Koch Membrane. It's now called Koch Separation Solutions for about 25 years. And we're based out of Wilmington, Massachusetts. And I'm going to open this PowerPoint up, and you tell me if you can see it. Is that being shared now, Jim?
Not yet, no.
No, okay. Back here.
There we go.
There it is now. Okay.
Yeah.
Excellent.
Can you make it full screen, Jack?
Yep, let's see.
There we go. That's great.
That working? Okay. So we're based out of our headquarters is in Wilmington, Mass. So we manufacture all of our membranes in Wilmington. We also have our sales, marketing, accounting, QC is all done in Wilmington. And we also have systems manufacturing operations just outside of Toronto and Minneapolis. We have sales offices pretty much all over the world. And in Wilmington, we make a wide variety of membranes. We make ultrafiltration, reverse osmosis, microfiltration, nanofiltration, in many different formats. Submerged hollow fiber, pressurized hollow fiber, tubes, and spirals. And the product that we're going to be talking about today is called the Puron MP ultrafiltration membrane, and that's pressurized hollow fiber membrane. This next slide shows some of the custom and standard systems that we manufacture. The three systems shown on the top are all used for wastewater treatment. So we have some MBR systems, membrane bioreactors, that are used to treat either industrial or municipal wastewater. We actually have a couple of small plants out in Western Mass, out in your neck of the woods. One at Vacation Village, right across from Jiminy Peak, treating some municipal wastewater, and then one at the Berkshire School. And then as you look down at the bottom, we have Targa 2 ultrafiltration systems used mostly for drinking water. The small package Puron MP system, which we proposed for your plant, and then reverse osmosis. So most of the UF systems are used in drinking water to remove suspended solids, either iron and manganese, or for surface water treatment to remove bacteria. And RO, you've probably heard of that before. It's used to remove dissolved solids. We actually have four plants in Massachusetts that treat iron and manganese. As Rick had mentioned, you need to oxidize those metals first, and then once the metals are precipitated, the membrane removes them very efficiently. We also have pilot systems. So with the Mass DEP, we might actually have to run a pilot to get their approval before we can install a plant. We can talk about that in the future, but we do have pilot units available to bring to the site and run some tests if we need to. And then once the system is installed, we have a KSS assist program where we can come out and monitor the equipment and do on-site visits to make sure everything's running well. We also can have remote data acquisition where we can evaluate the performance of the equipment remotely from our plant if you like that. And then we can assist with training if you have new operators. So just to get into the product itself that we're offering for this one, it's called the Puron MP. And it's a very unique product where the membranes are only potted at the top of the module. Those blue strands that are shown there are all the hollow fibers. They're free floating at the bottom. And then we put an enclosure around those cartridges and enclose them, and then we mount them on a skid. So that the skid that we've proposed for this one is called the Puron MP6. It has 6 cartridges on it, and that'll do the flows that Jim Erickson from Menard Engineering had given to us for your flow rates. So the fibers, they're reinforced fibers. You can't break them. It's an ultrafiltration membrane. If you're not familiar with the term ultrafiltration, the pores on the membrane are very, very small. If you're talking about micron size, if you look at the diameter of a human hair, it's about 40 micron. And these membranes, the pores are orders of magnitude tighter than that. They're at like 0.03 micron. So 1,000 times smaller than that. If you were to lay a membrane out, it looks like a sheet of paper. You can't see the pores, but they're there. And they only let dissolved solids through. No suspended solids will go through. So this next slide is just showing what's actually happening here. So we have, we'll call it the dirty water, flows in from the bottom of the cartridge. And under pressure, we force the water through the membrane, through those tiny pores, and all the oxidized manganese would be retained on the outside of the membrane. And over time, it would be build up. And what we do is then we do that little air scour. We scour the outside of the membranes and we back flush. So we would take some of that clean water that we just created, we send that back through the inside of the fiber and push it out and clean the membrane in that way. And then we drain out all those heavy solids, the manganese, and any other suspended solids out the bottom of the cartridge. And this is just showing that these free fibers, because they're able to kind of flow around inside that enclosed cartridge, all those solids are easily blown off and they can drain out very easily. Just some details on the membrane. It's a PVDF membrane, which is almost like a Teflon, so it's very inert. And we typically run these membranes upwards of 25 PSI and just force the clean water through. It can handle the chlorine, so if we're going to use some chlorine dosing to precipitate that manganese up front, it's still okay. It's not going to hurt the membranes at all.
Oh, I think that's like 900.
And this slide just kind of shows a very, very high magnitude picture of what those pores would look like. Those are the tiny little holes on the top and bottom in red, showing the under very large magnification what the pores would look like. And so the manganese would be orders of magnitude larger than that and just be retained by the membrane. So this shows the cartridge, how it operates. So we flow in from the bottom. The dirty water goes in the bottom, and then the clean water, once it passes through the membrane, comes out the top where it's to permeate out. And periodically, we do a back flush where we would send that clean water back through the membrane, and then all the solids would be drained out of the bottom. The back flushes are, anywhere, depends on how heavy a load it is. Anywhere between 20 to 60 minutes, we would perform that back flush, and it's all automated. So there's no operator involvement. It's all pre-programmed and very easy to operate, and the cleanings are done automatically as well. If we needed to dose in some chemicals on a back flush, we could do that as well, and we would determine the frequency of that during the pilot. And this is kind of a typical sequence of how it runs with air scour and permeate flow and back flushing. It's very simple. It's all programmed, and it runs unattended. These are some of the typical cleans that we might go through with an acid cycle to remove some of that manganese from the membrane surface, and chlorine to remove any bacteria that might build up over time. The cleanings are done for an application like this. We would call a CIP. It would be done maybe once a month, once every 2 months. Those cleaning chemicals, you need to figure out a way how we're going to dispose of those. That's a topic of discussion. So once we do that, we'd probably have to neutralize it and then dispose of them somehow, either in a tank, because I don't believe you have a drain to the sewer or anything that's close by. So we'd have to just put those in a tank and neutralize them and figure out a way to get rid of those. But that's a picture of the skid with the membranes running vertical. That's a back flush tank where we collect some of that permeate and then use it to back flush the membranes. On the right-hand side is a control panel with a PLC and HMI. And down at the bottom is the back flush pump that we would use, or recirculation pump. And all the connections are on the left-hand side, where we flow in and out of the skid. So it's a nice little package. This is a small skid for us with 6 cartridges, and we have skids that have 6 to 64 membranes on a skid. We can handle any flow that's required with multiple skids or in parallel, and handle flows from 20 gallons a minute to 20 million gallons a day. And I'll just leave it open for any questions that you might have.
Thank you, Jack. Do we have any questions from the audience?
Hi, this is Rick. There we go. Thanks, Jack. Rich Gullick here, the helping water quality specialist, I guess, instead of engineer. Do you have any data you can share or describe for us the manganese removal that your systems have exhibited at some other facilities for surface water treatment?
Sorry, I was muted there. Yes, we typically can get down below 0.03 for manganese levels. We've seen that on a lot of our plants.
What kind of influence in that case? We're hoping to get to a 0.015
Yeah, I don't think that'll be a problem. Based on the numbers that you had in the feed, our engineers said that should not be a problem at all.
Okay.
Okay, I have a question here from Margaret.
Yes.
Welcome, how are you?
Okay. I was just wondering how big that skid is. I mean, it's hard to tell because there's not a dummy standing next to it.
Yeah, the skid, the layout is like 7 feet wide and 15 feet long, and it's vertically about maybe 10 and a half feet tall.
Wow. And one of those could do like the town's water for a day, or?
Yep.
Wow.
Mm-hmm. Yeah, there's a lot of square feet of membrane area in one of those cartridges. It's 550 square feet. So,
okay.
Depending on redundancy requirements, if you need some redundancy, we might have to put 2 in. It depends on what the Mass DEP requires.
And will our water taste different after it's all cleaned up?
It shouldn't affect the taste. The membranes won't harm anything. They won't put in any flavor or anything like that. So if removing the manganese is a good thing, you should have better tasting water for sure.
Yeah.
We also may be able to reduce the amount of chlorine that we have to put in the water because of this system. Because in addition to the manganese, it removes what the slow sand filter would normally remove as well. And more, actually.
Mm-hmm.
So we may put less in, but we still need to maintain roughly the same level in the distribution system to keep the bacteria levels low. And we'll be adding less, but you may not necessarily experience much less. In that sense.
Right. Any other questions from the audience?
I'll mention, if I can, I'll follow up on that last question, big question. I believe that there is redundancy is required. So I believe the proposal that you've seen, Jim, has 2 units going in. They're rated for about 100 gallons a minute. That's about, I believe it's 147,000 gallons a day, almost 150,000 gallons right now. Your normal production is about 100,000 gallons a day. So it gives room to provide more water if so needed with a single unit. Then there's the second unit as a backup. So when that one is down for whatever reason, or if it just fails for whatever reason, which I'm sure it never will, yeah. But then there's a second unit to provide the water to the community.
Yeah, and just another comment about membrane life. These are not filters like you would have on an automobile or something where you have to replace them very often. These are going to last probably between 7 and 10 years. There's a very, very long life. So most of our plants in Mass have been seeing over 10 years life on their membrane.
It seemed a natural fit to do. When I first was looking at this and considering manganese removal and looking at different technologies, it seemed clear we were going to have to add a chlorine system, so we wouldn't use another oxidant, but we're probably going to add filters after the current filters. So that would have been rather expensive, basically the same thing as doing this, unless we put in sand filters and a lot of concrete. So this actually replaces the other one without too much additional cost. And upgrades that system. As I said before, there's nothing wrong with the performance of the current slow sand filters. They're really just a sandbox with water flowing through it, and they work quite well. But this technology will remove even more things from the water than the slow sand filters do. It's not microbiological like the slow sand filters. They have different performance.
Right.
But it should work excellently.
Right. So if you had any bacteria in the water too, you're going to get log removals of bacteria and viruses. So,
Jack, the manganese that we've seen in this water only comes during the warmer months. Typically late spring through early fall, primarily July to September. We would be able to shut the pre-chlorine off during the winter months, would we not?
Yes. Yeah.
Okay.
Jack, we also had a question from a customer regarding the wastewater and how that will be disposed of from the storage tank.
Yeah, so that's something we'll have to discuss. I'm not exactly sure. There's not a lot of generated, so it'll have to be neutralized, and we might be able to, once it's neutralized, put it back on the front end or something and treat it again.
Yeah. And
Well,
that,
we've got a lagoon there.
Okay.
That can be used for some disposal if allowed by DEP, with no adverse environmental impacts.
and this is information you would find if we did a pilot study.
Exactly.
Mm-hmm.
And what affects the amount of cleaning it needs? The quality of the water going into it, essentially?
Yes. So the dirtier the water, the more cleanings you're going to have to do. And it seems, based on the information that we've seen on your water, it's not bad at all. So it's going to be a very easy application for us.
And
It's a very clean source water. There's almost no development around that whole pond.
Yeah, we've done some applications where we're working on some really nasty river waters with high suspended solids and very high turbidities. And, we just have to pre-treat with some other flocculants to get those to drop out and then run the membranes and do more frequent back flushing than would be required here. So we're saying, you might have to do a back flush here once every hour. On a nastier application, the back flush would be, once every 10 minutes or something.
Jack, approximately of all the water that's brought into the plant from the pond, what percentage of it will not end up out distributed to the public? In other words, go out through the disposal.
Yeah, we're going to recover about 95% of that water.
Okay, so only about 5% is used for cleaning.
Mm-hmm.
Okay, that's a good number.
another question from a customer: how long have these systems been in operation?
We've been making membranes for 50 years. We have iron and manganese systems in operation in Massachusetts since '97. I think our first one was. That's in Littleton, Mass.
Okay. Another question: can these be added on to, say, the size of Housatonic doubles? Could you add another module on? I think you already answered that already.
Yeah, it would have to be a parallel system. We have larger systems in, if you thought the flow was going to increase, it might be worthwhile to look at, say, a system that had 10 cartridges on it and only install 6 to start. So you could just put on extra cartridges as needed. So if you think the flows are going to increase significantly over time, it might be worth looking at the larger skid and partially loaded.
Okay. Another question: is the manganese that is in the water hazardous? And if so, at what levels?
I'll take that one if you want.
Sure.
I can jump on that. It is not hazardous. The highest level that we've seen was a 0.1 part per million or milligram per liter. The lifetime health advisory is 0.3, and it'd be a whole 1 for a single day exposure. So we're well below any health advisories for it, but high enough that it affects the color. And so it's the color and the aesthetics that we're working to take care of. And that's based on all the data that we've seen so far. And often there's no manganese detected at all. The majority of the time it's not been detected. But during some of those July through September, and typically when the water is above 75 degrees, that's when we've seen it. It doesn't mean that all the water above 75 degrees has the manganese, but all the water that had the manganese was 75 degrees or higher, or almost all.
Okay.
We can focus on those months.
I have a question. When will this system be installed? The process that we have now is we did a study by Cornwell that was submitted to DEP back in November for review. We haven't received any response from DEP on that report yet. And then in March, Leonard Engineering submitted this proposal to deal with the manganese and the slow sand filters, and there's been no comment on that. So after DEP reviews it, we'll go back and forth and again with the engineers to fine tune it, so to determine what's the best route to go here. And then after that, there's a period where this has to be submitted to the Department of Public Utilities for the financing. So time frame wise, I'm not sure when this would be approved, but as soon as after that's approved, then we are ready, we'd be ready to install this. There, again, I think that Jack mentioned, a lot of times DEP requires a pilot study, and this is something that we could do concurrently while these things are being reviewed. They bring the skid in, they set it up. Maybe you could address that a little bit, Jack, on that process and how that works.
Yeah, so the whole pilot process would take, we'd ship the unit from, would come out of Wilmington, Mass. We'd get it out to you in a day. It would take another day to set it up, and we could be running on water, within a couple of days. So it's very easy to run. Typically, Mass DEP wants to see 4 weeks of runtime on the membranes and collecting of the data. So we'd run it for a month. We'd show someone how to run it in case it needed any maintenance while we were gone, but we would operate it and view everything remotely and come out there as needed. But we wouldn't be there for the whole month.
Yeah. Where's your experience in Massachusetts with these pilot studies? They run for 3 months, 6 months, 2 years?
The pilots themselves, the first one, when we did it in Littleton, the pilot was, I would say it was 6 months. That was our first one. But we're going to do another project in Mattapoisett. We're going to start the pilot up on Monday, and that's going to last for 4 weeks.
What size system is that, Jack?
They have a plant that's 2 MGD.
So it's a pretty good size system.
Yeah.
2 million gallons a day.
Correct.
MGD. Yeah, two questions on the pilot studies, if I may. Mm-hmm. Having followed the data that we've been collecting for the last couple of years, 2019 basically didn't have any manganese show up to speak of, and didn't have big power episodes from manganese coming through the treatment plant at least. Hydraulic disturbances such as flushing might have stirred some up in the distribution system. What if no manganese shows up in the source water during the course of this pilot study? Will you be spiking with manganese?
If needed, we could add some manganese just to show the removal efficiency, but the goal would be to run the pilot during the summertime where you have a good chance of seeing the high.
So you're hoping for the manganese. A little irony there, isn't it?
Yeah.
But yeah, it's actually a very important part of the pilot studies to make sure that's there.
Right.
Okay. So with this, sometimes manganese is dissolved, and sometimes it is, of course, particulate, especially after it's been chlorinated, and sometimes it becomes colloidal and more difficult to remove. Does your ultrafiltration membrane with the pre-chlorination, will that remove colloidal manganese?
It will, yes. Anything that's suspended would be removed by the membrane, so the colloidal manganese would be removed as well. And any iron, if you mentioned the iron was probably not an issue here, but if there were any iron in there and it was oxidized too, that would be removed.
Yeah, absolutely. Manganese is the target, the iron goes with it.
Yeah, exactly.
Okay.
I have another question regarding Giardia. Giardia or beaver fever has been referred to as significant 30 years ago when the city of Pittsfield had a bad bout of disease because of it. And we have beavers, of course, at Long Pond, and the slow sand filters are one of the most effective ways to remove Giardia. Are you familiar with that? And could you comment on this system and how that would work, Jack?
Yes, we've seen log removals of Giardia on the range of 4 to 6 log removals. So it's very, very efficient at removing Giardia.
So for the lay person, you could break that down for the average customer?
Yeah, so Giardia, I'm not sure the specific size of the bacteria, but it's fairly large in terms of micron size, and the membrane pores is so much smaller that particular material could not pass through the membrane, so it's essentially removed 100%.
I think they're on the order of 10 to 15 micrometers.
Yeah.
But nobody quote me on that. I'd have to double check it.
And the membranes are about 0.03 microns, so orders of magnitude smaller.
They're much better. And in addition to, and that would be the main removal. In addition, enough chlorine has to be added after the filters, after the filtration, to kill another log of Giardia.
Okay.
Because there has to be a chemical disinfection there.
Yep.
So I believe, unless the state gives enough credit for it. So
I don't think they'll give you, full credit. So you still you need the chlorine addition afterwards.
So what he meant by log removal, I'll try to explain that pretty quickly. One log removal would be 90%. Two log removals would be 99%. Three log removal is 99.9%. You're required to remove 3 log of Giardia from the surface water. You get 2 log credit from the filters, and then you need another 1 log credit for chlorine disinfection for these filters. Some filters you get 2.5 log credit. Either way, you're talking 4 to 6 logs, so it would be 99.99% to 99.9999%.
Right.
Okay, you're talking at 1, 2, 3 orders of magnitude more, right, than what's required for the 2 log removal. So it's an improvement.
Yeah.
The slow sand filters are really good, but these are tighter in that sense.
If anyone has any other questions, please raise your hand. I don't see any more questions. Hold on. No, I think that's it. So going forward, as I said, we have this proposal is before the DEP to review, and once that's reviewed and we agree that this is the best approach, we'll be forwarding a financing package to the DPU to review. There'll be more meetings on this and plenty of time for more comments. Information that we receive from DEP will be available on our website. We'll also be putting this PowerPoint from Jack and Koch Industries on our website as well for people to follow. And let me just check one more time for questions. Seeing none, this concludes our first informational meeting for 2021. And thank you, everyone. And please, if you have any questions, feel free to email us or call us, and we'll try to get them answered for you. Thank you, Jack, and thank you, Rich, for coming to this meeting.
My pleasure. Thank you.
Take care.
Bye.